The first topic concerned is about distributed indexing. Say here for web scale indexing only, do not try this at home. It's because we're talking about handling a huge amount of data. The data size is so big that it's impossible to store everything in one machine, and therefore we need a cluster of machines to handle them, and each machine is called a node in the cluster. And the basic idea is that to let each node contain index of a subset of collection. And the hardest part is to decide this subset. And there are basically two kinds of strategies. One is we partition according to the terms. It's called term partitioned index, which means we make a partition of the term dictionary and store different subsets of terms on different machines. So when a new term comes in, the first thing to do is to decide on which machine that we should insert that new term. And we find the proper machine and create a complete posting list on that machine for this term. So with this solution, each machine contains a complete posting list of a subset of the terms. Okay, so this is one strategy. And the other one is to partition according to the documents. It's called document partitioned index, which means the documents are partitioned into different machines. Okay, a complete term dictionary is contained by every machine, but on each machine, for example, on the first machine, for each term, its posting list contains only the documents that are numbered from 1 to 10,000. On the next machine, we can still find that term, and that machine contains a subset of the posting list of all the terms, and that subset contains the next 10,000 documents, and so on and so forth. So practically speaking, we cannot really solve the problem by applying one single solution. Usually it's a combination of the two strategies. Okay, and that's about distributed indexing. Another topic is about dynamic indexing. So to implement a search engine, usually we have to deal with these two problems, that documents come in over time, and when a new document comes in, we need to update the posting list for terms that are already in the dictionary, or we insert a new term into the dictionary. And also the documents get deleted. So for insertions, if every time a new term comes in, we have to update the whole posting list, which can be a very, very long list. If we have to update that and we have to keep it sorted, it's going to be quite expensive. Means that it's quite slow, it takes time, and time is money. So one solution is like this. We maintain a main index in the database, and at the meantime maintain another one called the auxiliary index. Auxiliary means what? In Chinese, how we translate it, 叫辅助性的、附加的, some kind of additional index, which is supposed to be small, or say light. Okay, when a new document comes in, it comes into this auxiliary index first. We maintain all the new documents, or to updating all the posting lists in this light index first. And when a user's query comes in, when a user asks you to find something, we have to search from both indices. This is the main index, which is large, and this is the auxiliary index, which is small. If we only have to do insertions, we just do insertions to this light index. If we have to search something, we should search from both indices and merge the results and return to a user. Okay, it's only when at some time point when we think it's definitely necessary, that we will merge this auxiliary index into the main index, clean up this space, and get ready for the new documents. And there are two quite difficult problems to solve. One is when to re-index. It means how we're supposed to decide when is the best time for us to merge the auxiliary index into the main index. That's when to re-index. And the other one is how to delete a document. That is actually very complicated. The third topic is about compression. Although that storage is not a big issue today, still we would like to save space as much as we can. For example, how are we supposed to store those terms? One solution is very simple, to store those terms in an array of strings, right? To treat each term as a string, and we maintain an array of strings. That's one simple solution. However, how are we supposed to define that array? What is the size of that array? It doesn't mean the number of terms, but for each term, how long is this string supposed to be? Well, in this simple example, none of the strings is too long. However, if you look at the dictionary in some special field, you might find some strange English word that contains hundreds of characters. So it's going to be a big problem, right? If you define each string to be a string containing hundreds of characters, there's going to be a big waste of space, right? So a smart solution is this. First of all, let's remove those stop words. And that's the first step to save some space, but not much. Okay. And secondly, let's store all the words in one long string, one after another, so there's no space wasted. On the other hand, how are we supposed to find them? We need another array to store the positions of each word, or say the positions of their first characters. Okay, that's one way to do the compression, to save some space on storing all those terms. And the other thing is this. Let's try to do some compression on the posting list. For example, say we have a term computer, and this word appeared in documents number 2, number 15, number 47, and so on and so forth. So eventually, when the new documents keep coming, sooner or later we're going to get overflow. A normal integer will not be large enough to hold document numbers, right? And then we can use what? Unsigned int. Or if unsigned int is not large enough, let's try long. But it's going to get larger and larger, and sooner or later, long is not big enough, right? So a very smart solution to this problem is this. Instead of saving all those document numbers, we save another sequence of numbers like this. What are they? 2 is the number of the first document. And what is 13? 13 is actually 15 minus 2. It's the difference of the two neighboring numbers of the documents. So what is 32? 32 is actually 47 minus 15. So what is 11? 11 is the difference of these two big numbers. So these two big numbers are compressed into a relatively small number. And practically speaking, most gaps can be encoded with far fewer than 20 bits, and that solves the problem. And last topic is about thresholding. What is thresholding? What is the Chinese translation of thresholding? It's 阈值. Alright, 阈值, not 阀值. Thresholding means we set up a line and we only try to solve a portion of the problem instead of the whole problem. And the size of that portion of the problem depends on this threshold we define. We apply thresholding in two situations. One is the document. Instead of retrieving all the documents, we only retrieve the top X documents, where the documents are ranked by weight. Okay, and that X is a threshold. It's up to you to define. So the basic idea is that when a user searches for something and the search engine returns several pages of results, usually a user would only take time to go through the first several pages. For example, if you get like 2,000 pages of results, I don't think there's anyone who would really, go through those 2,000 pages one by one. Okay, so it's pointless to actually return all the results if there are too many results to be returned. On the other hand, we would like to make sure that all the important pages are returned, are displayed in the first several pages. And therefore, we have to be able to tell that which pages are the really important ones. And that is, a lot of researchers are working in the areas of ranking those pages. Different search engines would have different strategies on defining the weight of a document, and therefore they rank documents in different ways. And that's why with different search engines, you search the same word, you will probably get different results. Thresholding means we only care about the top X documents and simply abandon the rest. And therefore, the performance can get better, it runs faster. However, it might cause some problems, like it's not feasible for Boolean queries. For example, like AND, while we are searching not only computer, but computer and science, we might get a bunch of documents containing the word computer, another bunch of documents containing the word science, and we like to merge them together and to find the intersection. If we only retrieve a subset of one word, a subset of the other word, the intersection might be severely affected, and therefore we might miss some relevant documents due to the simple truncation. Truncation means we simply keep the top X documents and cut the rest. That's what truncation means. And thresholding is also used in another situation for query. That is, in case that the user passes in a very long sentence that contains many words, many terms, is it really necessary to find the intersection of all the terms? Well, the thresholding strategy tells us to sort the query terms by their frequency in ascending order, and then search according to only some percentage of the original query terms. So only search according to the top X terms, not the whole sentence. So what does it mean? The first question is, why do we have to sort them by their frequency in ascending order? Ascending means the term with the smallest frequency appears first. First means it is considered to be the most important word. Why? So now let's compare two terms, one with very high frequency and the other one with very low frequency. Which one do you think is more important? Well, if a term has a very high frequency, what does it mean? It means that there are many documents that contain this word, right? So this word appears almost in every document, just like stop words. So it's obviously less important, right? If a term has a very low frequency, for example, to be extreme, so the frequency of this term is only 1. What does it mean? It means that among all those documents, there's only one document that contains this term, which means this term really tells the difference of this query. So that's very important. So this is supposed to be the most important term in that sentence. Okay, therefore that's why by sorting the query terms by their frequency in ascending order, we're listing all those terms according to their importance. The most important one is listed first. Okay, so now when we run searching, we will not process the whole sentence, but instead we only process several percent of the terms. Okay, for example, if your user's input consists of 10 different terms and we sort them according to their frequencies, then it's up to you to set up the threshold. For example, if you set the threshold to be like 20%, then we will only search the first 2 terms. Okay, if you're not sure about whether or not this is sufficient, you may try another threshold number like 40%. Then we will obtain another set of documents, right? And we can compare the 2 results and check the difference. If the difference is not that significant, it means that the result is probably sufficiently good. So we can stop here. All right. And if the difference is quite large, then it means that we might have missed something. And let's try another percentage, which is larger, and say 80%. It's all up to you to set up the threshold value. All right. And that is all about thresholding.